So we're going to talk about a toolkit called Distrest, Distributed REST Services, and how we are using that at Endgame for some computer security related purposes, but the toolkit, as we'll describe, is not at all specific to security. It's a fairly general, simple and general purpose toolkit. A quick introduction.
So my name is Donaher. I'm a senior site reliability engineer at Endgame, and I help build services and infrastructure to support a couple of groups, but a lot of it is working around R&D services to ensure they scale and meet demand.
And I'm a threat research engineer at Endgame. Basically means I'm a data and software wrangler within our R&D organization. Endgame, we are a computer security company. We provide distributed endpoint security. Basically, if you go into a larger company, it has 1,000, 10,000, 100,000 Windows machines on its network. We have software that runs and does some basically monitoring for bad behavior, responding to bad behavior on the within systems, within the network of machines, and just sort of working to detect and respond to threats as they occur. And it's a mixture of on-premise and hosted components. And in this, we're going to talk about the toolkit that we're talking about here, Distrest. It's something that we are using internally, so on the hosted side, as well as for a lot of just data processing and internal pipeline uses. In some ways, kind of spiritually similar to Sebastian's Ketru work and the BioKepi stuff that he presented yesterday. We're going to talk about what led to the development of Distrest, what Distrest is, how it works, how we are using it personally, and then go into some of the infrastructure management things that have bubbled up around it. And then we'll close out with a demo, a brief demo, and some forward-looking thoughts. So Distrest started out as I guess the thing before, thanks. Mm-hmm. Before we started developing Distrest, the initial kind of impetus behind it was we have a few teams within R&D, but primarily, I'm going to talk about the data science and malware researchers. So on the data science side, interested in collecting lots of data, reducing it into various models to make decisions based on, in this case, say the goodness or badness of a given piece of software. And on the malware research side, having access to this large corpus of software so that we can identify, if a new threat emerges and it's somehow unique, we can analyze it, find out A, how we are doing in protecting against this new threat, and B, if depending on how we're doing, if we're not doing as well as we'd like, then how we can improve that, what sort of features we can pull out and watch for to be able to catch these threats or variations on these threats in the future. We're a relatively not a small business, but it's not large by any means, not huge by any means. So we have a relatively small crew supporting all of this. So we need to go in relatively quick time because researcher time is valuable. We need to go relatively quickly from prototype to experiment to moving things out into the real world, and we don't have a whole lot of time and people to do that. So within those groups, within data science and our malware research groups, and within the company in general, but specifically in R&D, there are a handful of different languages that are used. Python is probably the one that's used most predominantly. At least some of you, I imagine, are familiar. There are a lot of, every week there is a new machine learning project that pops up in the Python world. And from both a due diligence and interest perspective, people want to try them out. So there are a lot of domain-specific tools and libraries that exist in these other languages, and they are, to varying degrees, they're either necessary or useful for our colleagues' jobs. So we want to make sure that they can do what they need to do as efficiently as we can help them do it, and to the extent possible, integrate these existing tools into their research. They can derive. One of our data scientists can drive their own research. They can do their own experiments. But once it goes beyond something that will run on, say, a laptop or a single machine, we want to make sure that they don't really have to change much or anything, hopefully, to take that from running on one machine on a few cores to spreading it over 50 or 100 different machines, to take that from a initial prototype to a now we want to see how this works when we throw 100 million different pieces of software at it. So we're trying to get the most performance that we can out of these research prototypes. We want to go, it's much cheaper for us, in effect, to spend 10 times the amount or 10 times the amount of computational power on a problem than it is for us to spend 10 times the amount of a person's time on a problem. In doing so, we want to change as little of their code as possible. So we don't want to, again, we want to take this core that has been tested and works at least for some subset of the problem and get that run that against our entire corpus of data as quickly as we can and be flexible in the process. So this kind of changing as little code as possible, and a few other aspects of the system kind of drove us, we have the idea that we want to scale by adding more instances first. Like I said, we want 10 times the CPU power, not 10 times the person time. And then if we are going to make modifications to the code, make them at the edges so that we are changing the way different applications communicate with one another. So this is all, if it sounds like we're talking about a microservice type setup, it is a very microservice type setup. So the drive behind this, the problems that arise from this kind of approach are pretty common to any similar type of setup. And again, we have, we want to take go from prototype to experiment, and that experiment existing, and for a number of reasons I'll get into, a few big reasons that I'll get into in a few slides. We want to take these existing tools, turn them into services, and do this all with minimal change. Because regardless of whether we individually think that they're the right tool for the job, regardless of an individual's personal feelings about Python, for example, or how unwieldy it might feel, it is the right tool for the job because it is allowing the people who need to get things done, get the things they need to get done. So ultimately, we want to ease experiments. So if we get a project to the point where again, it doesn't fit on one machine to do the experiments that need to do to prove out its utility, then we want to make it as easy as we can to perform experiments to make sure that when a new model is developed, that it's answering the questions that we want it to answer in the way that we want it to answer. So in our case, we're trying to test the goodness or badness of a piece of malware. I don't know if you've seen this example before, but there was a cool project that somebody put up, and you could draw, they had a few different things on the page, and you could draw a little sketch outline, and based on a bunch of inputs of different types of things, they had cats, they had shoes, they had buildings, I think. So you could do your little sketch with a mouse, and it would give back what it thought that thing should look like. But if you feed in a sketch of, a bad sketch of a cat, and you're giving it to information about shoes, you get kind of a weird looking cat, and that's not necessarily that, well, maybe amusing, it's not that useful. So we want to make sure that when we're trying to identify features, identify the goodness and badness of something, that we are really asking and answering the questions that we think we are asking and answering. So this brings us to Distrest, which is kind of a core tool that we've been using to enable all of this. It's an RPC-like REST toolkit, so it provides routing from HTTP-like responses to services that are distributed across a number of hosts. They can be running on the same machine, but they can be running on the same machine. They can be running on 5 different machines, 100 different machines. They can be running in different Docker containers across operating systems. And the key thing here is that because we are trying to go relatively quickly from prototype to a full-scale experiment, or in some cases full-scale production, we would like to minimize the impact of instability in a particular system. So if there is an edge case that isn't caught, we need to know about that. But we don't want the entire experiment to stop just because we hit an edge case that wasn't handled, an exception that wasn't caught properly in in a bit of Python or Go somewhere. The implementation is intentionally very simple. So we have 3 languages that we support on the service implementation side: OCaml, Python, and Go. Between all 3 of the core of the service, and then those 3 languages supporting libraries, it's approximately 2,300 lines of code. So it's a relatively small code base, relatively easy to get into and muck around with when we do need to make tweaks. There's a broker or proxy program written in OCaml. A small library, kind of the core of the library in each case is under 200 lines of code with a few support functions to go along with it to ease people's lives. And we actively use this on Linux, Mac OS, and Windows, both from the daemon side and from the proxy side and on the service implementation side. Schematically, this is how the process works. So we have HTTP clients calling in. A user of these services will be sitting over here, making their requests with curl or with a library in their language of choice. They'll call to the broker process, and then that broker or proxy has a handful of 0MQ sockets that it uses to speak back and forth with each service implementation. And we can have, say you have a service that's set up to get some data and another service that's set up to post some data. Those services can live, because we're using the 0MQ sockets here, those services can live wherever you want in the network. They can live on the same machine or they can live on different machines. As long as they can communicate back and forth with one another over these handful of ports. There are 2 ports. But as long as they can communicate together over those ports, then everybody's happy. So this part is in OCaml, about 1,900 lines of code. It's using LWT for its concurrency, co-HTTP to speak HTTP to the outside world, and 0MQ, like I said, to talk to the services. And the services are written in a handful of different languages and potentially growing at some point. Another part of the toolkit that we use pretty heavily is a dispatch service, which we'll probably rename because there's already a dispatch on OPAM. But it's a tool to process dependency graphs between services. So you can say these services generally are kind of moderate to high latency. Moderate being tens of milliseconds, high latency being tens of seconds. To early experiments, there are some that were minutes, but generally we're kind of going up to tens of seconds right now. But something that if a human is sitting in front of it, when they're that expensive, there's generally a human sitting on the other side waiting for a result. So we want to be able to chain these services together actively so that you can make a request, have data propagate through some set of steps that are required for processing, extracting data, saving it off to a database. As dependencies are resolved, we can process these steps in parallel. So the submissions are made concurrently, and then the different machines running them can run the actual requests, perform the requests in parallel. And this won't be part of the initial. It still needs more cleanup and pulling out from our internal code base, but this is going to be released as part of our Distrest package. For us personally, our 2 main uses, kind of core uses for this are, well, early on it was extracting and aggregating metadata about binaries, so Windows PE files, DLLs, EXEs, pulling out a bunch of features that our researchers can use to create their models, train their models, test their models. And then eventually, at this point, that has become a key part of our offering to our customers. A tool called Malware Score, which is just it's a rating of the goodness or badness of a particular piece of software. So if it comes in, this machine learning model, which is behind the scenes, it's a boosted decision tree, basically a game of 20 questions looking at different features in in the binary. So one of our biggest, I guess, throughput uses of this is we have a fire hose of data coming in the door, and we want to extract all of the features from it. So early on, they're blanked out because some of the names were crazy, but this is kind of an early example, an early experiment dependency graph that we would work with. The light orange nodes are, they have no dependencies, so they would get whatever the raw submission is to this dispatch graph, and then the blue nodes receive whatever the aggregate input is of their of the upstream services, whatever their dependencies are. So in this case, we could run the 4 orange nodes concurrently. Once this one finishes, these 4 can all run concurrently, and once this over here finishes, this can run concurrently. It's a relatively simple case. As experiments developed to be more complex, and we want to compare a bunch of different things, you end up with something that looks more like this. A happy little simple process running over here. But then you can see these are a nice little star here. You basically have a bunch of different, not necessarily variations of the same features or the same tasks, but multiple iterations or variations of each feature that we're looking at in a particular binary, in a particular sample. And all of those getting aggregated and stored into some central data store here so that we can come back later and run experiments against these variations and these different options, see what combination of features gives us the best result. We also use this, like I said, we found it to be, or may have said, we found this tool set to be generally usable beyond just our initial supporting experiments around data extraction. So we have this as kind of our front end to storing and extracting or storing and retrieving rather our malware and benign-ware corpus. We have a bunch of data coming in the door after deduplication and some other filtering. This data store is growing by approximately 5 terabytes a month. So if we want to keep any sense of that, we need to make sure that it is that those are all organized in a sane way rather. So the service is there just to kind of make sure that everybody lands where they need to land and that we know that everything's indexed properly. And we also use it to proxy out to external services. So there are a bunch of external services that, or a handful of external services that are of different uses to us. Sometimes they're really expensive to call out to, and if the results of those calls have a long shelf life, then we can cache them internally, serve them back to users. We don't have to. We can provide an easier interface because some of them are relatively complex, and our uses of them are relatively straightforward. In general, in the case of dispatch in particular, the purpose of the service is to take. I didn't mention this earlier when I was introducing it, but in aggregating the data from upstream sources, it kind of bundles everything together currently into one JSON blob. We're going to add support for message pack as well for better handling of binary data. But you could use this to say, if you have a handful of sources or sites or any handful of sources that you wanted to scrape in a general sense, you could make all of those, add all of those into a graph, and then have as all of their dependencies a downstream store, so Elasticsearch or some other data store that can receive JSON directly, and Chris will demonstrate that in our demo in a few minutes. So it makes it very easy to collect and aggregate these kinds of inputs. Because of the way the communication works, we get some load balancing for free. It's a first come, first serve as far as requests go. So whoever comes in and says, I can handle that first, will get that request. But if one instance can't handle all the requests, then other ones will step up to pick up the slack. The key thing here is that, like I said, these are a lot of what we're working on are either high CPU or other for other reasons, high latency requests. So if for whatever reason it's easier to write something serially and then spin up 10 of them, we can write it serially and spin up 10 of them and get 10 times the throughput. And there's no extra configuration required. You stick your broker on one machine, you stick your services wherever they need to go. As long as they all point to the same instance of the broker, they can receive the same requests. Then they'll all load balance automatically with no extra configuration. And then for us, we're dealing with a lot of malware. A lot of that is Windows malware. And we need to analyze this in some cases on Windows machines. So we want to keep those isolated. This gives us a nice bridge to run these analyses on Windows in an isolated network and only have kind of a narrow channel out of there that we can carefully monitor and make sure nothing's going to break free and spread the next worm. And now I'm going to turn it over to Chris to talk about
Thank you.
infrastructure.
So anybody have any questions on the first part before I take it away? All right, awesome. So as Hez already mentioned, you can kind of see that the initial examples were kind of small. Those graphs that were blue and pink, I guess, were fairly small graphs, and then they were growing out. So you can see that we kind of had an increasing need to take services that were prototypes running on like a single really beefy box with a couple hundred gigs of RAM or whatever, to move that across a bunch of hosts. And so that's kind of where the site reliability engineer organization came in. There's a bunch of things that we kind of ran into simultaneously. I'm sure all of you that have microservice infrastructures run into this as well, is that you are developing a bunch of libraries kind of in lockstep. And if you're not careful, versions get out of sync. Or if you're distributing services but not distributing them well, you run into single points of failure and just whole parts of your infrastructure go dark. Or just being able to scale if you need to go like reprocess a large amount of data, or if you need to go handle increased request load from external sources. Those things all kind of are a problem. And then if you're not careful, you're going to end up in some situation where you catastrophically lose a trust or whatever terminology people use. So we ended up using Kubernetes. Now, Hez mentioned that this can run on a variety of platforms, OS X, Linux, and Windows. And I want to continue to emphasize that. The reason that we looked at using Kubernetes is because we need to spin up hundreds of these containers to handle request load and also to add like a level of resiliency. So we spread hundreds of these containers, instances of our distressed daemon and services that subscribe to it across numerous hosts, kind of abstract away the layer of the hardware. And as you can see, Kubernetes is a big kind of unwieldy abstraction sometimes. It's a ship that carries ships that, I guess, carry shipping containers. So there are a couple of caveats with running the distressed daemon, the distressed server in Kubernetes, predominantly when it comes to routing traffic to the instances, the distressed instances, versus the services. Because we have two types of communication that communicate with the server and then also the services, they kind of need to be able to speak differently. And that usually just, we have to model session affinity differently. So clients that are contacting our distressed daemon, that was on the left side of that blue box from the first graph, have no session affinity. We don't care which instance of the distressed daemon they communicate with. Subsequent requests should get load balanced across multiple distressed daemons as fairly and evenly as possible. However, we need to make sure that our distressed services always communicate with the same distressed instance. So for example, if a request comes in, goes to the distressed instance, and it tasks some service A, and then service A says, OK, now I need to send a response somewhere, but it doesn't necessarily know which distressed server to send to, the client's going to see a timeout. They're going to see some sort of error because the communications bridge between the services and the distressed daemon has been broken. So that's a small caveat. So we're going to go over a small distressed OCaml service. I know a lot of you are more Haskell inclined. The syntax is fairly readable, and we're going to go over it in pieces. And the thing to notice is that the boilerplate to turn OCaml code into a compatible distressed service is minimal. It's two things, really. It's a verb and a path to accept. So if you're used to RESTful request verbs, put, post, patch, delete, get, those are the types of verbs we're looking for. And then a path. So we can match relative and or exact and prefix paths, but we'll get into that later. And then you also have to define a handler function, which accepts a request and returns a response. And so we'll go over that in steps. But first, type signatures, since everyone loves type signatures here. Your path definitions are fairly straightforward. You specify a co-HTTP method, which just is the verbs that we were describing, gets, posts, etc. And then a string, which represents the path. So this is very similar to if you're setting up handlers and whatever web micro framework you fancy. It just specifies the path of the server that we're going to be targeting. And you can either specify an exact path or a prefix path. And then we specify a run, which the only things that we really want to point out are the path declaration, the path.t, and the callback function, which is the function that we're going to define here. Whoop, let me go back. So here's the request handler that we're going to define. Suffice to say, this thing just takes in a post request and returns some metadata about that post. Returns an ID of the instance of the Distrest service, returns the number of requests that the instance has responded to. This will be more relevant in the demo. The MD5 hash of the content, timestamp, size in bytes, and duration. The only thing to notice here is that these are the parts, the tiny red circles there, here, and here are the only pieces that are specific to the Distrest framework. It's just the input type is a request, and the response type is just a JSON string marshaled to a response. And then this is the main. And so you can see that we have the run function that we just previously talked about in the path. Here, these red boxes that are, again, very thin, we define the verb and then the path. So in this example, we just call our service count service, very original. And then we point it to a count service handler here. And so here's the whole thing. That's the service that defines it. Now, as we said, there's only a very few pieces that actually are Distrest specific, and the clients for the other languages, the Python client and the Go client, are similarly minimal. Yeah, here with arrows. All right, so now we're going to run through a demo showing how the service works. First, we're going to show how the service works, and we're going to see kind of how the handshake between the Distrest service and the Distrest daemon occurs. And then we're going to walk through a simple dispatch graph, which is that blue and pink or blue and orange connecting of services. And then we will show scaling up the number of services that subscribe to a Distrest daemon in Kubernetes running on my laptop, which is nice for prototyping, but I wouldn't recommend it for anything else. All right, so I don't know if...
Do you need to move it over to the other display, maybe?
What?
Because I don't think it's mirroring.
Oh, OK. So I guess we can maybe... Oh, right. Yeah, let me move my tmux session to the right. All right. Sorry, bear with me a second.
If you drag that over.
Oh, I have to drag this.
That, yeah. Or whichever direction. Yeah, there you go.
OK, great. OK. This is a 3-pane tmux session that's a lot smaller over here. It's like a vision test for me. All right, excellent. So right now we have 3 panes. On the leftmost pane, we're going to run the Distrest server. And that's the piece that handles requests from services. We're going to run it in as verbose mode as possible so we can kind of trace what's occurring. And hopefully is this visible for most people? I know it's kind of small. So you can see we start it up. We have some just simple debug messages and say that it's listening on some sockets. And the next thing we want to do is start up the count service here that connects to the service. These things, either piece of this, the distressed daemon or the subscribing service, can die, and they will recover when the next piece recovers. So we start this service here. We see a bunch of things happen. One, we see that the service itself acknowledges that it connected to the distressed daemon. And then we see this info piece right here that says that the distressed daemon is acknowledging that we have a new path that's sent from the service to the distressed server. So it says we can accept post requests to this path. And finally, what we're going to do is we're going to curl a simple post to the service and get a response. So you see a bunch of things happen in quick succession. We see that the distressed daemon acknowledges the request, tasks the task to this service, and then the service handles it, prints out the response as just debug information, and then we get the return, which we can, I guess we can pipe to JQ if you all fancy actually reading that JSON. Yeah, so you can see the total number of requests is 2, the number just incrementing. That'll be useful for the next piece, the dispatch graph. You can see that the ID doesn't change. This is a basically concatenated UUID of the service. OK, so that's all well and good, but say we want to compose multiple of these services using dispatch graph. We want to take the response from a request and pass it to another service. For that, we'd want to use the dispatch service that Hez previously mentioned, and it's somewhere in this history. So here, let's put it on the other pane. So here's a very simple dispatch graph. It's just a JSON document that describes like a graph of services. You'll notice here that this deps is an empty array. That means that this is the entry point of your dispatch graph. Dispatch graphs are named when they're loaded into the dispatch service. And whenever you post, this is the entry point that accepts the binary or payload. You can have multiple entry points, and they all accept the post at the same time. And then you can see here that this deps array now has this ID in it, which says that we're basically taking the response from this request, and we're passing it here. This service that we haven't really gone over yet is just a simple elk stack. It's Elasticsearch with some visualization. And this shows that we can basically say, I want to take this JSON that we just saw from this curl and pass it through to Elasticsearch. So we're going to kick off a long-running stream of requests to our service. And we're going to look at running this in Kubernetes. So this is JQ, and it's malfunctioning because, I guess, tmux. But what we're going to do next is go look at what is happening in Kubernetes and also in the elk stack. Where was it?
It's maximized.
Where?
That one's maximized.
So we're going to look here. And so one thing to know is we only have a single instance of this count service running. So we can go look here at this. This resolution's all terrible. So we're going to just look at a video. How about that? We have a video of this thing. And we'll have to. You'll have to trust me that the rest of this thing works live. Right, so inside Kubernetes, we're going to gloss over the vast majority of what actually occurs in Kubernetes. For the sake of this talk, the only thing that really matters is that we have the concept of a replication controller that can expand the number of services that we have just kind of on the fly. Right now, we only have a single instance of the counter service running. And so we can basically demonstrate that no results are coming in. But then once we start streaming those requests through, you'll start seeing results show up. And as previously described, we only have a single instance of the service running at a particular time. And then what we can say is, say we want to expand the number of services kind of organically. We can go here, and we can just type in a new number. So we can say like 10. You can also use an API to expand the number of services we have. You can see that they're increasing. These things are pending. But as they start up, we'll see that they're starting to accept connections and get distributed tasks. And this is all because the responses from the dispatch graph are being passed through from the first count service to the elk stack container. Nope. So we're going to go back to the presentation now. And we're going to have to abridge it because there is. All right, so spoilers for jokes. We've run into a variety of development challenges around maintaining services that connect to Distrest. We have to maintain the Distrest daemon in addition to all the client libraries. And anytime we change the server, we introduce kind of breaking changes to the comms protocol that it communicates with these client libraries, which means that you kind of have to maintain them all in lockstep, which ends up being a little bit like juggling a bunch of things at once. It's kind of a pain. And then, of course, there's always external resource contention. So even if we can indicate that we can scale up to 10, 50, 100 instances of a particular service that are all reliant on some NFS mount or some database, you don't really fix the scalability problems of whatever you're relying on. If you're talking to an external API that rate limits you or goes down, then you're really only as good as the weakest link. And sometimes it feels like this, trying to catch fish, but sometimes they get through. So as Hez mentioned previously, we're going to be open sourcing the Distrest framework and the dispatch service on GitHub. We have a couple of outstanding to-do items that we'd like to get done in the near future. One is to implement streaming requests and responses. So we want to be able to chunk up large files. Since we're sending binary files that can be quite large, it ends up spiking RAM usage really regularly. And we also want to open source the dispatch service and implement WebSockets and ZRMQ as client interfaces to kind of negate the TCP connection overhead of the HTTP requests. And here's some resources. These things aren't currently populated. We're still waiting on a few things before we can open source it, but very soon. And so I can be reached at cdonaher@endgame.com, and Hez can be reached at hcarty@endgame.com if you would like to contact us. Are there any questions? No? Okay. We're tight on time, but yes?
Do you have any notion of pressure?
Not currently implemented.
No, yeah. So in general, we've tried to keep, like I said, keep things as simple as possible. And if there is a case where we need back pressure, we've been leaning more on failure and allowing the client to come back later, in effect.
Yeah, I think Hez might have mentioned that we propagate failures up and we don't retry requests either. So the proxy does very little logic to try and recover. If a failure occurs on one of the services, it will just propagate the failure up, and the onus is on the client to restart the connection to retry the request.
We have time for maybe one more question. Okay, thank you, Chris and Hez.
Thanks.
Thank you.